Our universe is unimaginably old and vast, yet its earliest chapters remain its most profound secrets. We will journey back to the very beginning, to the first fleeting instants after the Big Bang, and explore 25 of the greatest mysteries from the dawn of time. You will gain a complete picture of the cosmic puzzles that define our origins, from the nature of dark energy to the birth of the very first stars. We will confront questions about what sparked existence itself and why the cosmos is built the way it is. What do you believe is the universe's most enduring secret? The biggest question of all is also the first one. What triggered the Big Bang? It is important to clarify a common misunderstanding. The Big Bang was not an explosion that happened at a single point in an empty void. Instead, it describes the moment our entire universe, all of space and time itself, began expanding from an incredibly hot and dense state. Think of it not as a firecracker going off in a room, but as the room itself, the very walls and floor and ceiling, suddenly and rapidly inflating. Everything we see today was contained in that initial, unimaginably compact seed. But what caused that seed to exist in the first place? This is where our physics breaks down completely. As we rewind the cosmic clock, the universe gets hotter and denser until we reach a point called the Planck epoch. This is the first fleeting fraction of a second, a duration so short it has almost no meaning in human terms. Here, the known laws of gravity and quantum mechanics collide and cease to make sense. Our equations point toward a singularity, a point of infinite density and temperature. But infinities in physics are usually a sign that our theories are incomplete, that we are missing a deeper rulebook. So, what could lie beyond that singularity? One leading idea is cosmic inflation. This theory proposes that a tiny patch of space, perhaps born from a random quantum fluctuation, was filled with a strange form of energy. This energy caused that patch to expand faster than the speed of light, smoothing it out and stretching it into the vast, uniform cosmos we see the seeds of today. Inflation elegantly explains many features of our universe, but it still leaves us wondering what created that initial patch and its strange energy. Other theories suggest our universe is part of an endless cycle, a cosmic heartbeat where a previous universe collapses in a big crunch only to rebound in a new Big Bang. Or perhaps our universe is just one bubble in a vast, frothing multiverse, where new universes are constantly budding off from an eternal background. The profound and humbling truth is that the concept of before may not even apply. If time itself began with the Big Bang, asking what came before is like asking what is north of the North Pole. It is a question framed in a language that no longer works. So the first great mystery is not just about a starting gun, but about the very nature of existence, a puzzle where the rules we rely on to solve it vanish at the moment we need them most. This invisible scaffolding brings us directly to our second great mystery. What exactly is dark matter? We know it is there because the universe behaves as if it is filled with something we cannot see. Take a spiral galaxy like our own Milky Way. Stars on the outer edges orbit the galactic center at speeds that should, according to the visible mass of stars and gas, send them flying off into the void. The fact that they do not tells us there must be a huge amount of additional mass holding them in place, mass that does not emit or reflect any light. This same story repeats on a colossal scale. When we observe massive clusters of galaxies, we see their gravity bending the light from more distant objects, a phenomenon called gravitational lensing. The amount of bending is far too strong to be caused by the visible galaxies alone. A vast, unseen halo of matter must be wrapped around them, its gravity shaping the very fabric of space. This dark matter is not a minor component. It makes up roughly 85% of all the matter in the cosmos. In the early universe, it played the lead role in building everything we see. After the Big Bang, ordinary matter, the protons and neutrons that make up stars and planets, was a hot, scattered plasma pushed around by the pressure of light. Dark matter, however, is thought to be cold and sluggish, unaffected by light. Its gravity acted first, pulling together into vast, invisible webs and clumps. These dark matter wells became the gravitational pits where ordinary matter could finally pool, cool, and eventually ignite into the very first stars and galaxies. Without this dark foundation, the cosmos would be a formless, dim sea of gas. So what is this ghostly substance? The leading candidate for decades has been a theoretical particle called a WIMP, which stands for Weakly Interacting Massive Particle. As the name suggests, it would be heavy and interact with normal matter only through gravity and perhaps the weak nuclear force, making it incredibly difficult to catch. Teams of scientists have built ultrasensitive detectors deep underground, shielded from cosmic rays, hoping to hear the faint ping of a WIMP colliding with an atom. So far, the detectors have remained silent. Another intriguing possibility is a particle called the action, predicted to be incredibly light but existing in such vast numbers that their combined mass could explain dark matter. Experiments are now using powerful magnetic fields to try and convert these elusive actions into detectable microwaves. The truth is, we have built an entire cosmic history on the gravitational effects of something we have never directly touched or seen. It is the most dominant form of matter in the universe, and yet it remains a name for a set of observations, a placeholder in our equations. Solving this mystery would not just identify a new particle, it would rewrite the story of how our universe assembled itself from nothing but the faintest whispers of gravity in the dark. Yet for all its power to pull the cosmos together, dark matter is locked in a cosmic tug of war with a force of repulsion. This brings us to the third and perhaps most baffling mystery. What is dark energy? If dark matter is the invisible glue holding galaxies together through its gravity, dark energy is the opposite. It is a mysterious pressure that is pushing the universe apart, and its strength is increasing as space itself expands. The story of its discovery is one of the great surprises in modern science. In the late 1990s, two independent teams of astronomers were measuring the distances to extremely far-off exploding stars, called Type 1, a supernova. These stellar explosions are remarkably consistent, acting like standard candles that allow us to gauge cosmic distances. The researchers expected to find that the expansion of the universe, set in motion by the Big Bang, was slowing down over time due to the collective gravity of all the matter within it. It was like tossing a ball into the air, expecting gravity to eventually bring it back down. Instead, they found the ball was not slowing down at all. It was speeding up, accelerating into the sky. The distant supernova were fainter than they should have been, meaning the space between us and them had stretched more than anyone predicted. Something was actively working against gravity, driving the galaxies apart at an ever-increasing rate. This something was dubbed dark energy. Today, measurements tell us that dark energy constitutes about 68% of the total energy content of the cosmos. Dark matter makes up about 27%, and all the stars, planets, gas, and dust, everything we can actually see amounts to a mere 5%. So dark energy is not just a curious side effect, it is the dominant component of the universe, dictating its ultimate fate. The leading explanation is that dark energy is the energy inherent to empty space itself, an idea Einstein once proposed and then discarded as his greatest blunder. In this view, even a perfect vacuum is not truly empty. It seethes with quantum fluctuations, virtual particles flickering in and out of existence. This vacuum energy could produce a repulsive force, acting as a cosmological constant that stretches the fabric of space. But here we encounter a profound and unsettling puzzle known as the coincidence problem. When we calculate what the energy of the quantum vacuum should be based on our theories of particle physics, the number is absurdly, catastrophically large. It should be 1 followed by 120 zeros times stronger than what we actually observe. If it were that strong, the universe would have been ripped apart before the first atoms could ever form. The observed value of dark energy is not just a little off, it is infinitesimally tiny by comparison. Even stranger is its timing. For billions of years after the Big Bang, the universe was dense and matter's gravity dominated, allowing galaxies to form. Dark energy was present but insignificant, like a whisper in a storm. Only relatively recently, in the last 5 billion years or so, as the universe expanded and thinned out, did dark energy's push finally overcome gravity's pull and begin to accelerate the expansion. Why did it become dominant just as intelligent life emerged to observe it? Is this a bizarre cosmic accident or a clue to a deeper law we do not yet understand? The nature of dark energy determines the final chapter of our universe. If it continues as a constant force, it points to a cold, lonely end where galaxies fly apart beyond the cosmic horizon, leaving islands of stars isolated in an ever-darkening void. But if it changes over time, the future could be far more violent or perhaps even cyclical. We are left observing a force that controls the destiny of everything, born from the emptiness between the stars, and we have no idea why it has the gentle yet decisive strength that it does. The universe's acceleration is a mystery of its future, but its ancient past holds a paradox of its own, one written in the faint afterglow of creation. If you look at the cosmic microwave background, the oldest light in the universe, you will find a map of stunning, almost boring uniformity. This relic radiation, released when the universe was only 380,000 years old, has nearly the same temperature in every direction we look. The variations are incredibly tiny, mere millionths of a degree. This uniformity is the problem. According to the standard Big Bang model, the universe had not existed long enough for light or heat to travel from one distant region to another. Think of 2 cups of coffee placed on opposite sides of a vast, cold room. If they are both steaming hot, you would assume they were recently poured from the same pot or that someone carried heat between them. But in the early cosmos, the room was expanding so quickly that the 2 coffee cups, representing regions on opposite sides of the sky, could never have exchanged heat or information. They were forever beyond each other's cosmic horizon, yet mysteriously they are exactly the same temperature. How could parts of the universe that were never in contact agree on such a precise thermal state? This is the horizon problem. The leading and most elegant solution is a concept called cosmic inflation. It proposes that in the first fraction of a second after the Big Bang, the universe underwent a brief but staggeringly rapid expansion, ballooning in size by a factor of at least 10 to the 26, far faster than the speed of light. This does not violate relativity because it was space itself that was stretching, not objects moving through space. During this inflationary burst, a tiny, subatomic patch of space that was once in thermal contact was stretched to become larger than our entire observable universe. What we see as opposite sides of the sky today were once neighboring points in that tiny, uniform seed. Inflation smoothed out any wrinkles, erased any drastic temperature differences, and set the stage for the remarkably even cosmos we observe. It is a powerful idea that solves the horizon problem beautifully, yet inflation itself remains a theoretical framework. While it makes specific predictions about the pattern of tiny fluctuations in the cosmic microwave background, which our observations have confirmed with remarkable precision, we still do not know what caused it or what that strange inflationary energy truly was. We see the smoothed-out result, the perfectly level plaster on the cosmic wall, but the tool that did the smoothing, the trowel of inflation, is still hidden from our view. Its verification requires us to probe a realm of energy 1 trillion times more powerful than anything our particle colliders can reach, leaving this elegant solution as one of the most compelling, yet still unproven, chapters in the story of our origins. This profound uniformity is only half of the puzzle. Look deeper, and you find the cosmos possesses a geometric perfection that is equally improbable. The universe is flat. This is not flat like a sheet of paper, but flat in the geometric sense, meaning the rules of Euclid we learned in school, where parallel lines never meet and the angles of a triangle add up to exactly 180 degrees, apply on the grandest of scales. This geometric flatness is a direct reflection of the universe's density. Imagine space itself can have one of three possible shapes, dictated by the battle between expansion and gravity. If the density of matter and energy is too high, gravity wins. Space curves in on itself like the surface of a sphere, a closed universe where parallel lines eventually converge. If the density is too low, expansion wins, creating an open, saddle-shaped universe where parallel lines eternally diverge. But if the density is precisely the critical value, the balance is perfect, resulting in a flat Euclidean geometry. Our most precise measurements, from the cosmic microwave background to the large-scale structure of galaxies, all tell us we live in that perfectly balanced, flat universe. And that presents a profound mystery known as the flatness problem. The trouble is that a flat universe is incredibly unstable over time. Any tiny deviation from perfect balance in the early moments would have been magnified exponentially as the cosmos expanded. Think of trying to balance a pencil perfectly on its tip. The slightest tremor, the tiniest breath of air, will knock it over. For the universe to be as flat as we see it today, 14 billion years after the Big Bang, its initial density must have been fine-tuned to an astonishing precision of 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. The odds of this happening by random chance are essentially 0. It is as if the universe was born already knowing the perfect recipe for flatness, set with a dial of unimaginable precision. Once again, the theory of cosmic inflation provides a compelling answer. The ultra-rapid stretching of space during that first fraction of a second would have acted like a cosmic iron, smoothing out any initial curvature. No matter what shape the universe started with, whether slightly closed or slightly open, inflating it by such a colossal factor would have made it appear flat to any observer within it, just as the surface of a balloon appears flatter and flatter as you blow it up to an enormous size. Inflation naturally drives the universe toward that critical density, solving the fine-tuning problem by making flatness the expected outcome, not a miraculous accident. Yet this elegant solution deepens the mystery of what powered inflation itself, leaving us to wonder if the geometric perfection we observe is a fundamental feature of reality, or merely the lasting signature of a force that vanished almost as soon as it began. This perfect geometric balance was forged in an era of unimaginable violence, a time when the universe was a seething sea of particles and their ghostly opposites. We exist because of a slight cosmic favoritism in that ancient war. The sixth great mystery asks, why is there more matter than antimatter? According to our best theories, the Big Bang should have produced perfect symmetry. For every quark, the building block of protons and neutrons, an antiquark should have been created. For every electron, a positron. Matter and antimatter are identical in mass but opposite in charge, and when they meet, they annihilate each other in a flash of pure energy. In a perfectly balanced early universe, every particle should have found its antiparticle, resulting in complete mutual destruction. The cosmos would have been left as a fading bath of radiation, devoid of stars, planets, or life. Yet here we are, in a universe made of stuff. Clearly, something tipped the scales. For every billion pairs of matter and antimatter particles that annihilated in the first second, one solitary matter particle survived. That tiny 1 in a billion asymmetry is the reason everything we see exists. It is the ultimate cosmic surplus, the residue of creation. Physicists call the process that created this imbalance baryogenesis. To make it happen, three strict conditions had to be met in the early universe, conditions first outlined by the scientist Andrei Sakharov. First, there must be a violation of something called charge parity symmetry, or CP violation. This is a fundamental rule that says the laws of physics should treat particles and their mirror image antiparticles the same way. If this symmetry were perfect, matter and antimatter would behave identically and no excess could ever form. We have observed small amounts of CP violation in certain rare particle decays, but it is far, far too weak to account for the vast amount of matter we see. The early universe must have hosted a much more powerful process that favored matter. Second, there must be a violation of baryon number. Baryons are a class of particles that include protons and neutrons, the heavy constituents of atoms. In our everyday world, baryon number is conserved, meaning you cannot just create or destroy a proton out of nothing. But in the extreme energy of the early cosmos, this rule must have been broken, allowing a net number of baryons of matter particles to come into being. Third, all of this had to occur while the universe was out of thermal equilibrium. Think of a pot of water coming to a rolling boil. The chaotic, bubbling state as it transitions is out of equilibrium. If the universe had remained perfectly smooth and balanced during this critical phase, any matter excess created would have just been wiped out again. It needed a moment of chaotic change to lock in the advantage. The search is on for the physical process that satisfied all three conditions. Experiments like those at the Large Hadron Collider at CERN are smashing particles together at near light speeds, recreating conditions a fraction of a second after the Big Bang. They are looking for any hint of new particles or interactions that could have tipped the primordial balance. Some theories point to the decay of incredibly heavy, hypothetical particles in the first instance after inflation. Others suggest the asymmetry might be tied to the behavior of neutrinos, those ghostly particles that barely interact with anything. The mystery of baryogenesis is not just a question about the past, it is a question about our own existence. We are the evidence of that ancient, 1 in a billion break in symmetry, living proof that the universe, for reasons we still do not understand, preferred substance over shadow. That 1 in a billion surplus of matter gave the universe its building blocks, but for hundreds of millions of years, those blocks lay dormant in an era of profound darkness. The seventh mystery asks, what were the first stars like? After the cosmic microwave background faded, the universe entered what astronomers call the Dark Ages. It was a simple, monotonous place. Space was filled with a cool, diffuse fog of hydrogen and helium gas, the only elements forged in the Big Bang's first minutes. There was no light, no structure, no complexity. The cosmos was waiting for a spark. That spark came from the first generation of stars, known as population 3 stars. They were unlike anything that shines today, born from clouds of pristine, pure hydrogen and helium, completely free of heavier elements, or metals as astronomers call them. These stars could grow to staggering sizes. Without metals to help the gas clouds cool and fragment efficiently, the collapsing clouds simply kept gathering more and more material. Current theories suggest population 3 stars could have been behemoths, hundreds of times more massive than our Sun. Imagine a star so colossal it would make our Sun look like a pebble beside a mountain. These giants would have burned with a ferocious blue-white intensity, living fast and dying young. Their lives, perhaps only a few million years, were a cosmic blink, but they changed everything. Inside their searing cores, the alchemy of the universe truly began. Through the process of nuclear fusion, they cooked the primordial hydrogen and helium into heavier elements. For the first time, carbon and oxygen were forged, the very elements essential for planets and life. They also created nitrogen, silicon, and iron. When these short-lived titans finally exhausted their fuel, they did not go quietly. They collapsed and exploded in cataclysmic supernova of unimaginable power, far brighter than any supernova we see today. These explosions did two crucial things. First, they blasted those newly forged heavy elements out into the surrounding gas, polluting the cosmos with the seeds of future generations. The second generation of stars, population 2, would form from this slightly enriched material. Second, their intense ultraviolet radiation blasted through the cosmic fog of neutral hydrogen, ripping electrons from atoms in a process called reionization. This began to clear the haze that had filled the universe, ending the dark ages and making space transparent to light, a state it has maintained ever since. So why have we never seen one? Their extreme distance and brief lifetimes make them incredibly elusive. They shone for only a moment, cosmically speaking, over 13 billion years ago. Finding their light is like trying to spot a single, distant match flame from across an ocean. But now we have a tool designed for this very hunt, the James Webb Space Telescope. With its infrared eyes, Webb can peer back to those earliest epochs, looking not for the stars themselves, which may have already exploded, but for their unique signatures. It searches for the chemical fingerprint of their metal-free supernova or the specific glow from the hot gas they helped ionize. Discovering direct evidence of population, 3 stars would be like finding the fossilized remains of the universe's very first life forms. They were the pioneers, the violent, brilliant architects that transformed a dark, simple cosmos into a complex one rich with the potential for everything that followed. Those first stellar explosions seeded the cosmos, but they also left behind something far more enigmatic. Scattered across the early universe were the corpses of those massive first stars, black holes containing perhaps a few dozen times the mass of our Sun. Yet when we point our telescopes back to when the cosmos was less than 1 billion years old, we find something that defies all reasonable growth charts. We see quasars, the brilliant beacons powered by supermassive black holes that are already billions of times the mass of our Sun. This is the 8th great mystery. How did supermassive black holes form so quickly? The timeline simply does not add up. A stellar mass black hole born from a dying star grows by pulling in or accreting surrounding gas. But this process has a speed limit known as the Eddington limit. If a black hole eats too fast, the intense radiation from the infalling material actually pushes the surrounding gas away, choking off its own food supply. Even if a black hole feasted continuously at this maximum rate, it would need many hundreds of millions, if not billions, of years to reach the colossal sizes we observe in the infant universe. It is like finding a fully grown, 1,000-year-old redwood tree in a forest that is only a decade old. Something had to give these cosmic monsters a colossal head start. One compelling theory is called direct collapse. Imagine not a star dying, but a giant cloud of pristine hydrogen gas, left over from the dark ages that never fragmented into stars at all. In a region devoid of the heavy elements that help gas cool, this vast cloud, perhaps containing the mass of 100,000 suns, could have collapsed directly under its own immense gravity. It would have bypassed the star stage entirely, plummeting straight into a massive black hole seed, a behemoth born with a weight of tens of thousands of solar masses already on the scale. This seed would then have a huge appetite from day one, allowing it to grow rapidly into the supermassive giants we see. Another possibility is that the earliest stellar black holes merged together at a frantic pace inside dense, young star clusters, quickly building up mass. Or perhaps the first black holes were able to break the Eddington limit, gorging on gas in brief, chaotic feasts where the physics of the early universe allowed for a more efficient, messy consumption. Each of these theories has profound implications for how galaxies themselves formed. We now believe that a supermassive black hole lies at the heart of nearly every large galaxy, and the mass of the black hole is strangely linked to the mass of the galaxy's central bulge of stars. This suggests that the birth and growth of the black hole and the galaxy are deeply intertwined, each regulating the other in a cosmic dance that began in those first chaotic epochs. Did the black hole form first and guide the galaxy's assembly with its fierce gravity and radiation? Or did the galaxy's rapid formation funnel a feast of gas directly to a waiting seed? The James Webb Space Telescope is now hunting for the answer. Its powerful infrared vision is finding more and more of these incredibly distant early quasars, pushing the record back to when the universe was only a few 100 million years old. It is also searching for the fainter, more elusive signatures of those hypothetical direct collapse black hole seeds, objects that would be massive but not yet brilliant quasars. Solving this mystery is key to understanding the powerful engines that shape the cosmic dawn, lighting up the darkness with their impossible, voracious fire. The brilliant glow of those first quasars did more than signal the birth of black holes. It helped tear apart the very fabric of the cosmic dark. The universe was about to undergo a fundamental change of state, entering its ninth great mystery, the epoch of reionization. For hundreds of millions of years after the Dark Ages, space was filled with a pervasive fog of neutral hydrogen gas. The atoms were whole, with their protons and electrons bound together. This fog was opaque to certain wavelengths of light, particularly the high-energy ultraviolet light that the first stars and quasars began to blast out. But that intense radiation carried enough power to rip the electrons away from their protons, ionizing the hydrogen and turning the fog into a transparent plasma. Think of a dense morning mist blanketing a valley. As the sun rises, its rays burn through the fog in patches, creating clearings of blue sky that gradually expand and merge until the entire valley is bathed in sunlight. Reionization was that process on a cosmic scale, but the suns were the first stellar populations and quasars, and the valley was the entire observable universe. The key questions are profound. What were the primary sources of the ionizing radiation? Was it mostly the fierce ultraviolet light from those massive population 3 stars? Or did the brilliant quasars powered by their supermassive black holes do the heavy lifting? Or was it a coordinated effort with stars ionizing their local neighborhoods and quasars with their piercing beams reaching out to clear more distant pockets? And how did this process unfold? Was it swift and uniform or slow and patchy, with bubbles of clear, ionized space growing irregularly around clusters of early galaxies before finally overlapping? Astronomers pieced together this story by using the most distant quasars as cosmic backlights. As the light from a quasar more than 13 billion light-years away travels toward us, it passes through the intergalactic hydrogen from that ancient era. If that hydrogen is still neutral, it will absorb specific wavelengths of the quasar's light, creating a thicket of dark absorption lines in its spectrum known as the Lyman alpha forest. But if the hydrogen along the path has been ionized, the light passes through freely. By studying the spectra of many quasars at different distances, and thus from different times, astronomers can map how the fog lifted. They can see when the absorption forests begin to thin, indicating the bubbles of ionized gas are growing, and when they finally disappear, marking the moment that epoch concluded, around 1 billion years after the Big Bang. This was the universe's final major transition, the moment it became the clear, transparent expanse we observe today. Understanding reionization is understanding the end of the universe's childhood, the point when it became permanently illuminated, its basic structure set for the eons of star-making that would follow. The universe cleared its skies, but the story of dark matter was far from over. While its gravity sculpted the grand spirals and majestic clusters we see, its influence on the smallest scales presents a glaring conflict. Our 10th mystery confronts a problem of missing dwarfs, a mismatch between prediction and observation known as the missing satellite problem. According to our most sophisticated supercomputer simulations of cosmic evolution, which model how dark matter clumps under its own gravity, a galaxy like our Milky Way should be surrounded by a vast swarm of smaller dark matter halos. These halos are the gravitational seeds for dwarf galaxies, small, faint collections of stars. The simulations are clear. They predict thousands of these satellite halos should be orbiting our galactic home. Yet when we look up, we only see a few dozen. It is a staggering discrepancy. Where are all the missing dwarf galaxies? One possibility is that we simply have not seen them yet. Many of these predicted satellites could be so faint, composed of so few stars, that they blend into the darkness of intergalactic space. They might be dominated almost entirely by dark matter, with only a handful of ancient stars flickering within them. Recent sky surveys have indeed discovered several new ultra-faint dwarfs, each a ghostly smudge of light pushing our count higher. But even with these discoveries, the number remains far below the simulated thousands. The satellites are missing, or they are hiding in plain sight. Another line of thought suggests that maybe our understanding of dark matter itself is incomplete. The standard model assumes cold dark matter, particles that move sluggishly, allowing them to clump efficiently from the very beginning. This produces the abundant small halos our simulations predict. But what if dark matter is warm? Warm dark matter would consist of lighter, faster-moving particles. This extra motion would act like a kind of pressure, smoothing out the smallest density fluctuations in the early universe. It would prevent the very tiniest dark matter clumps from ever forming, naturally reducing the predicted number of small satellites. The large-scale structure of the cosmic web would look similar, but the fine, dusty spray of tiny halos would be absent. This is an elegant solution, but it must be tested against all our other observations. Or perhaps the satellites did form, but they were destroyed. The early Milky Way was a violent place. Tidal forces from our galaxy's immense gravity could have ripped apart these fragile dwarfs as they swung close, scattering their stars into the galactic halo and leaving behind only dark, starless clumps of matter. Our galaxy's history may be written in these ghostly streams of stars, the shredded remains of ancient satellites we can now detect. The missing satellite problem is more than a counting exercise. It is a direct test of our core model of cosmic structure formation. Do we need to tweak the properties of the mysterious dark matter that makes up most of the universe's mass? Or do we need to better understand the complex, messy astrophysics of how, or if, stars can ignite within the smallest, darkest clumps of all? The answer will determine whether our cosmic neighborhood is as crowded as the simulations insist, or if the darkness around us is even emptier and stranger than we thought. That cosmic fog of dark matter halos predicted but unseen is not the only ghostly imprint on our sky. Look closely at the map of the cosmic microwave background, the baby picture of the universe, and your eye might be drawn to one particular feature. In the southern constellation of Eridanus, there is a patch of sky that is just a little too cold. This is the 11th mystery, the cold spot. It is not a tiny blemish. This region spans a staggering 1 billion light-years across, a colossal anomaly in the otherwise remarkably uniform afterglow of the Big Bang. While the rest of the CMB shows only minuscule temperature fluctuations, this area is noticeably cooler by about 70 microkelvins. That may sound trivial, but statistical analysis suggests such a large, cold region is extraordinarily unlikely to occur by random chance in our standard model of cosmology. It is a cosmic bruise that should not be there. So what could have left such a mark? The leading conventional explanation is a supervoid. Imagine an immense bubble in space, a region of extraordinarily low density containing far fewer galaxies and clusters than the cosmic average. As light from the cosmic microwave background travels through such a void, it must climb out of this gravitational well. According to Einstein's theory of general relativity, light loses energy as it climbs against gravity. This energy loss stretches the light's wavelength, making it appear cooler and redder to an observer on the other side. This integrated Sachs-Wolf effect could, in theory, produce the cold spot we see. It would be a shadow cast by a truly vast emptiness, a billion light-year-wide cosmic hollow. Astronomers have searched for this proposed supervoid. They have found evidence of a large underdense region in that general direction, but its size and emptiness do not seem sufficient to fully explain the pronounced coldness of the spot. The void is there, but it might be too shallow to cast such a deep shadow. This leaves the mystery wide open. When conventional explanations fall short, more exotic ideas emerge. One captivating possibility is that the cold spot is a cosmic texture. This is a theoretical defect in the fabric of space-time, a kind of knot or wrinkle that could have formed during a phase transition in the very early universe as it cooled from an ultra-high-energy state. Think of it like the cracks that form in ice as water freezes. If such a texture existed and we passed through it, it would leave a distinct circular temperature imprint on the CMB, a signature that matches what we observe. Even more mind-bending is the suggestion that the cold spot could be evidence of a collision with another universe. During the inflationary period, our universe may have been one bubble among many in a vast multiverse. If our bubble bumped or brushed against a neighboring one, the energy of that collision could have left a permanent circular scar on our cosmic microwave background. In this scenario, the cold spot is not a shadow or a defect, but a bruise from a primordial encounter with a separate cosmos. The truth is, we do not yet know. Follow-up observations have been tantalizing but inconclusive. The supervoid exists but seems inadequate. The exotic theories are compelling but currently untestable. The cold spot remains an enigmatic fingerprint on the oldest light we can see, a reminder that our standard model, for all its success, might still be missing a few pieces of the puzzle. It is a quiet, cold challenge written across a billion light-years, waiting for a deeper observation to finally reveal its origin. The oldest stars in our galaxy are cosmic time capsules, preserving the chemical makeup of the universe in its infancy. Their atmospheres should contain a specific, predictable amount of lithium, an element forged not in stars but in the first few minutes of the Big Bang itself. This prediction comes from our highly successful model of Big Bang nucleosynthesis, which accurately forecast the cosmic abundances of hydrogen, helium, and deuterium. The chart is a testament to this success, with the predicted bars for those light elements lining up almost perfectly with the observed bars from ancient stellar data. But there is one glaring exception. For lithium-7, the predicted bar is about 3 times taller than the observed one. The universe, according to these pristine old stars, contains only a third of the lithium it should. This is the lithium problem, a stubborn mismatch between our elegant theory of creation and the fossil record written in starlight. Why does this tiny discrepancy matter so much? Because Big Bang nucleosynthesis is a precision test of the universe's first minutes. It is a straightforward calculation based on the known density of protons and neutrons and the rapidly dropping temperature of the expanding cosmos. Getting hydrogen and helium right gives us tremendous confidence in the whole model. Lithium is the most fragile of these primordial elements, and its predicted abundance is exquisitely sensitive to the conditions of that early nuclear soup. A factor of 3 error is not a minor rounding issue. It is a signal that something in our picture is incomplete. So where did the lithium go? One possibility is that our understanding of the stars themselves is flawed. Perhaps these ancient stars have internal processes we do not fully account for, mechanisms that slowly drag surface lithium down into their hotter interiors where it is destroyed. Over billions of years, this could deplete their atmospheres, hiding the true primordial amount. Astronomers search for the coolest, most pristine stars where such mixing should be minimal, yet the lithium deficit persists. Another avenue points back to the beginning. Could new, unknown particles have been present during those first few minutes? Certain theoretical particles, like hypothetical types of neutrinos or particles associated with dark matter, could have altered the nuclear reaction rates just enough to produce less lithium-7 without upsetting the perfect agreement we see for hydrogen and helium. This would be a direct window into physics beyond the standard model, etched in the chemistry of the first stars. Or perhaps the answer lies in between, in the long journey from the Big Bang to the star we observe today. Could primordial lithium have been destroyed by some early astrophysical process before these oldest stars even formed? The mystery endures because each solution creates new challenges. Adjusting the nuclear physics risks ruining our perfect predictions for the other elements. Invoking stellar destruction requires processes efficient enough to work universally, yet subtle enough to leave no other obvious mark. The lithium problem is a quiet but persistent whisper from the dawn of time, a single note out of tune in an otherwise harmonious symphony of creation, reminding us that even our best stories of origin may still have missing pages. Lithium's quiet discrepancy is a puzzle of chemistry, but a far more dramatic pattern stares back at us from the cosmic microwave background itself. The 13th mystery is known rather ominously as the axis of evil. It is a name that captures just how unsettling this finding is to the foundation of modern cosmology. The principle of isotropy states that the universe on the largest scales should look the same in every direction. There should be no special axis, no preferred plane, no cosmic north or south. Yet, when scientists analyze the largest ripples in the CMB, the subtle temperature differences that seeded all future structure, they find a bizarre and controversial alignment. These vast billion-light-year waves appear to be curiously oriented with the plane of our own solar system. It is as if the echo of creation knows which way Earth is tilted. This should be statistically impossible. The chance of such an alignment occurring randomly in an isotropic universe is incredibly small, like rolling a die 100 times and getting the same number every single time. So what are we seeing? The most conservative explanation is that it is a fluke, a statistical anomaly that will vanish as we gather more precise data. The universe is vast, and sometimes improbable patterns do emerge purely by chance. Another possibility is that it is not a feature of the cosmos, but a ghost in our machine, a systematic error introduced during the complex process of subtracting foreground signals from our own Milky Way galaxy. If we are not perfectly cleaning our data, a residual smudge from our galactic neighborhood could imprint a false axis on the map. Yet, after years of analysis and data from multiple satellites, some features of this alignment persist, fueling a more radical line of thought. Could it be a relic of something before inflation? The theory of inflation was invented to explain the stunning uniformity of the cosmos, ironing out any pre-existing wrinkles. But what if inflation did not start from a perfectly symmetrical point? What if there was some primordial structure, a directional preference etched into the fabric of space-time before the inflationary expansion began? That initial fingerprint, stretched to cosmic proportions, could potentially leave a faint, preferred axis imprinted on the entire observable universe. The axis of evil represents a deep philosophical rift in cosmology. Is it a warning that we are still seeing the universe through a dirty window, our view contaminated by local astrophysics? Or is it a genuine crack in the cornerstone of isotropy, a hint that the universe has a fundamental handedness we have yet to understand? The debate is fierce because the stakes are the Copernican principle itself, the idea that we do not occupy a special place. This alignment, if real, suggests that on the grandest scale, the universe might just know we are here. This unsettling alignment challenges a core pillar of cosmology, but another discrepancy threatens to rewrite the cosmic rulebook entirely. The rate at which the universe is expanding, known as the Hubble constant, is a fundamental number that sets the scale for everything from the age of the cosmos to its ultimate fate. For decades, astronomers have worked to pin down its exact value, and today we have two supremely precise yet stubbornly conflicting answers. This is the Hubble tension, and it is arguably the most urgent crisis in modern cosmology. The conflict is stark when you look at the measurements side by side. On one hand, we have the early universe method. By studying the detailed pattern of the cosmic microwave background, the afterglow of the Big Bang, the Planck satellite mission could calculate how fast the universe was expanding in its infancy. Using our well-tested model of cosmic evolution, which includes dark matter and dark energy, they could then extrapolate that expansion forward to predict what the rate should be today. This method gives a value of about 67 kilometers per second per megaparsec. This means that for every megaparsec, which is a distance of about 3.26 million light-years, a galaxy appears to be moving away from us 67 kilometers per second faster. On the other hand, we have the local universe method. Astronomers use cosmic lighthouses like Cepheid variable stars and Type I, a supernova, to measure distances to nearby galaxies with incredible precision. By comparing these distances to how fast the galaxies are receding from us, measured by the redshift of their light, they get a direct present-day measurement of the expansion rate. This local measurement, led by projects like the Hubble Space Telescope and the SH0ES team, consistently gives a higher value, around 73 kilometers per second per megaparsec. The difference is only about 6, but given the tiny error bars on each measurement, the gap is statistically huge. It is like two world-class archers, each with perfect aim, consistently hitting two different bullseyes on the same target. One set of measurements is looking back at the infant universe to predict the present, while the other is taking a direct snapshot of the present itself. They should agree, but they do not. This tension suggests that our standard model of cosmology, lambda cold dark matter, might be incomplete. Perhaps dark energy is not a constant but evolves over time, strengthening in recent cosmic history to give the expansion an extra kick. Maybe there is a new, unknown type of neutrino or other relativistic particle that was zipping around in the early universe, subtly changing the sound waves imprinted on the CMB. Or perhaps there is something we do not understand about the dark matter itself. The more mundane but crucial possibility is that there is a hidden systematic error in one of the measurement chains. Maybe our understanding of Cepheid stars has a subtle flaw, or the cosmic distance ladder has a rung we have not calibrated perfectly. Teams are now using new methods, like observing the gravitational waves from colliding neutron stars, to provide a completely independent check. The Hubble tension is not just a disagreement over a number, it is a potential doorway. If it persists, it means our cosmic timeline is wrong, our understanding of the universe's contents is flawed, or that physics itself behaved differently in the past than we have assumed. The entire edifice of modern cosmology is waiting to see which measurement, if either, will finally yield. The Hubble tension reveals a crack in our cosmic model, but to find its source we must look back to the time when the universe first switched on its lights. The end of the Dark Ages was not a single event, but a slow, patchy dawn. We know the fog of neutral hydrogen was burned away by a flood of energetic ultraviolet photons, a process we call reionization. But the identity of the cosmic arsonists remains hotly debated. Who or what provided the immense energy needed to strip electrons from atoms across the entire cosmos? The prime suspects are the first generations of stars. Those massive, metal-free population 3 stars would have been prodigious producers of hard ultraviolet radiation. In dense clusters, their combined fury could have blown vast, growing bubbles of ionized gas into the surrounding neutral fog. Yet there is a problem of timing and efficiency. These stars lived very short lives and exploded quickly. Could their brief, brilliant flashes have sustained a global reionization process that lasted hundreds of millions of years? The other major suspect is the first black holes, not the supermassive ones powering brilliant quasars, but smaller, accreting black holes in the cores of the earliest dwarf galaxies, sometimes called mini-quasars. A black hole feeding on gas releases a torrent of high-energy X-rays and ultraviolet light, and it can keep doing so for as long as there is fuel. A population of these smaller, persistent engines might have provided a steadier, more penetrating ionizing background, their radiation reaching further into the cosmic voids. There is even a more exotic possibility. What if the energy came not from astrophysical objects at all, but from the decay of exotic particles left over from the Big Bang? Certain theoretical particles, like those predicted by some dark matter models, could have decayed during this epoch, releasing a smooth bath of ionizing radiation. This would be a fundamental particle physics solution to an astrophysical mystery. The challenge is that we cannot simply look back and watch it happen. The era of reionization is too distant, and the neutral hydrogen itself blocks the very ultraviolet light we need to see. Instead, astronomers are detectives looking for circumstantial evidence. They search for the earliest, faintest galaxies, the likely homes of both massive stars and small black holes. They measure the rate at which these galaxies form stars and estimate how many ionizing photons they could have produced. They also look for the shadowy fingerprints left on the light from even more distant quasars, mapping where the hydrogen fog has been cleared. This is where the James Webb Space Telescope is revolutionizing the hunt. Its infrared eyes are perfectly suited to find the redshifted light of those first galaxies. In its deep field images, it is not just finding a handful of bright specks, it is revealing a universe already teeming with tiny, faint galaxies when it was only a few 100 million years old. The sheer number of them suggests that perhaps it was not a few brilliant giants, but a vast population of small, faint galaxies that provided the collective ultraviolet glow to end the darkness. Each new crimson smudge in a JWST deep field is a candidate for a reionization engine, a pocket of stars working to clear the cosmic haze. By counting them, measuring their brightness, and analyzing their light, we are beginning to piece together the story of how a dark, simple universe transformed itself into the transparent, star-filled expanse we call home. These faint early galaxies did more than just shine. They may have woven invisible threads through the cosmos. While stars and black holes filled space with light, another, more subtle force was being born. The 16th Great Mystery asks, where do cosmic magnetic fields come from? Today, we know that magnetic fields are everywhere. They thread through the spiral arms of galaxies like ours, guiding cosmic rays and influencing how stars form. They permeate the vast spaces between galaxies in clusters, shaping the hot gas that glows in X-rays. But in the very beginning, the universe was likely born without any magnetic fields at all. The smooth, hot plasma of the Big Bang would have had no structure to generate them. So how did these weak but pervasive fields emerge, and when? This is a classic chicken and egg problem for the cosmos. One school of thought argues for a primordial origin. In this view, incredibly weak seed fields were generated in the extreme conditions of the very early universe, perhaps during the phase transitions that occurred just after inflation. These fields would have been unimaginably faint, trillions of times weaker than the magnetic field of the Earth. But as the universe evolved, these tiny seeds could have been stretched and amplified by the motions of ionized gas, a process similar to how a dynamo works. In a cosmic dynamo, the rotation and turbulence of a galaxy or cluster can take a small magnetic field and twist it, stretch it, and feed energy into it, boosting its strength over hundreds of millions of years. The seed provides the initial direction, and the dynamo does the heavy lifting. The opposing idea is that magnetic fields are an astrophysical byproduct generated much later by the first stars and supernova. When a massive star explodes, it creates shock waves that can generate magnetic fields through a process called the Biermann battery. This effect occurs when there is a misalignment between the pressure and density of a plasma, creating electric currents that spawn magnetic fields. The violent outflows from these first supernova could have flooded their surroundings with newly minted magnetic fields. which were then carried out into intergalactic space by galactic winds. These fields would later be captured and amplified as new galaxies formed. Detecting the fingerprints of a truly primordial field is one of the toughest challenges in cosmology. A field generated in the Big Bang would be imprinted on the entire universe, having a coherent structure on the largest scales. Astronomers search for its signature in the subtle polarization of the cosmic microwave background light, or in the way it might affect the propagation of the highest energy cosmic rays as they travel across the universe. So far, the evidence is elusive. The fields we see today could have grown from either type of seed. Their importance, however, is undeniable. Magnetic fields are not just passive tracers, they are active players. In galaxies, they provide pressure that supports gas clouds against collapse, slowing down star formation. They channel and accelerate particles to near light speed, creating the cosmic rays that fill interstellar space. On the largest scales, magnetic fields in galaxy clusters can influence how the hot cluster gas swirls and mixes, and even how galaxies within the cluster interact. Solving the mystery of their origin would tell us if magnetism is a fundamental property woven into the fabric of space-time from the first moments, or a later innovation, an emergent feature of a universe that learned to make stars and explode them. It is the search for the first whisper of a force that now shapes the cosmos. These pervasive magnetic fields are a later innovation, but the first stars were the original cosmic alchemists. Their lives were spectacularly brief, and their deaths even more so. The fate of a population 3-star depended entirely on its immense mass. Current models suggest they could have formed with masses ranging from a few tens to several hundred times that of our Sun. This staggering weight changes everything about how they live and die. A star like our Sun will burn for billions of years and end as a quiet white dwarf. A population 3-star, a true cosmic titan, faced a far more dramatic and violent end. For the most massive of them all, those between about 140 and 260 solar masses, death came in a uniquely catastrophic event called a pair instability supernova. In the final moments of such a star, the core becomes unimaginably hot. This heat spawns a runaway process where gamma-ray photons, the very energy holding the star up, spontaneously convert into pairs of electrons and positrons. This conversion robs the core of its supporting pressure almost instantly. The result is not a gentle fade, but a total, unstoppable collapse. The core implodes, triggering a thermonuclear explosion of such ferocity that it completely unbinds the star. Nothing is left behind, no black hole, no neutron star. The entire stellar body is vaporized in a blast of light that can outshine an entire galaxy for months. Every atom forged in its heart, from carbon to iron, is blasted into the void in a final, glorious act of creation. For stars even heavier, above that 260 solar mass threshold, gravity wins in a different way. Their cores are so immense that not even a pair instability explosion can stop the collapse. They would bypass the supernova stage entirely, their entire structure plummeting directly into a massive black hole, swallowing their chemical riches almost entirely. The chemical fingerprint of these different deaths is the key to finding them. A pair instability supernova, by completely dispersing the star, would enrich the surrounding gas with a very specific mix of elements, one rich in iron but lacking others produced in more typical explosions. Astronomers now search for that unique signature in the spectra of the most ancient metal-poor dwarf galaxies orbiting the Milky Way. These galactic fossils are the archaeological sites of the early universe. If we can find a star in one of them with the precise elemental pattern predicted for a pair instability blast, it would be direct evidence of a first-generation star's final, world-ending act. The search is a hunt for the ashes of the very first fires, a forensic investigation into the explosions that lit up the cosmic dark and set the table for everything that came after. Those titanic explosions scattered the seeds of creation, but not every cloud of gas and dust was destined for stellar glory. Some gave birth to cosmic phantoms, galaxies so vast and yet so faint they almost vanish against the blackness of space. These are the ultra-diffuse galaxies, and their existence is a profound challenge to everything we thought we knew about how galaxies are built. Imagine an object the size of our Milky Way, with its majestic spiral arms spanning 100,000 light-years. Now imagine removing 99% of its 100 billion stars. What remains is a ghostly, translucent haze, a smear of ancient starlight so diffuse you could look right through it to the galaxies beyond. That is an ultra-diffuse galaxy. They are not small, they are enormous, but they possess only about 1% of a normal galaxy's stars, making them incredibly difficult to spot. For decades, they hid in plain sight, their faint light blending into the glow of the night sky. Their discovery in large numbers is a recent triumph of sensitive telescope surveys, which revealed whole populations of these spectral objects floating in galaxy clusters and in isolation. Placed side by side, the contrast is shocking. A classic spiral galaxy like Andromeda is a dense, bright whirlpool of stars, gas, and dust. An ultra-diffuse galaxy like Dragonfly 44, found in the Coma cluster, is a faint, ethereal blob of the same physical size, a cosmic jellyfish adrift in a sea of darkness. So how does something so big end up with so little stuff? The leading theories present two very different stories of cosmic failure. The first suggests these are failed galaxies, born in halos of dark matter that were starved from the beginning. Perhaps they formed in regions where the gas was too hot to condense efficiently, or where a nearby quasar or a torrent of radiation from other young galaxies stripped away their star-forming fuel before they could get started. They were stillborn, their vast dark matter halos never managing to gather enough gas to light up with a significant stellar population. The second theory proposes a more violent internal history. Maybe they started as normal, gas-rich galaxies, but experienced an intense, early burst of star formation. The resulting supernova, those titanic explosions from massive stars, could have blown the remaining gas completely out of the galaxy in a powerful galactic wind. With their fuel supply ejected, star formation would cease forever, and the existing stars, no longer held in a tight disk by the gravity of all that missing gas, would slowly drift apart, puffing the galaxy up into its current diffuse state. This is a galaxy puffed up by its own stellar feedback. Each explanation has consequences. If they are failed galaxies, they should be dominated by incredibly massive halos of dark matter to explain their size. Some observations support this, showing that a few ultra-diffuse galaxies have dark matter contents rivaling the Milky Way's. If they are puffed-up galaxies, their dark matter content might be more normal, but their stellar populations should show signs of that ancient, frenzied burst of star formation. The data is still coming in, and it suggests the answer may not be one or the other, but both. There might be multiple paths to becoming a cosmic ghost. Their very presence forces us to revise our models of galaxy formation, which traditionally linked a galaxy's physical size very tightly to its mass and star formation history. Here, that link is broken. They demonstrate that the universe can assemble matter on the scale of a grand spiral galaxy, but then, for reasons we are still deciphering, simply neglect to fill it with stars. They are the empty palaces of the cosmos, vast and ornate structures echoing with the silence of what might have been. While the universe built its ghostly palaces, it also generated flashes of radio energy so brief and brilliant they defy comprehension. In the span of a human heartbeat, a single mysterious event can release more energy than our sun emits in 80 years. These are fast radio bursts, and their origin is one of the most electrifying puzzles in modern astronomy. Detected as sharp spikes on radio telescope data, FRBs last mere milliseconds. Yet in that blink of an eye, they broadcast across cosmic distances so vast their light has been traveling for billions of years. The most distant ones we have detected come from galaxies so far away they existed when the universe was only half its current age, placing their source squarely in the epoch of reionization and galaxy formation. So what cosmic engine can possibly produce such a staggering, concentrated blast? The list of suspects is as exotic as the bursts themselves. The leading candidate is a highly magnetized neutron star called a magnetar. Imagine the collapsed core of a dead star, a city-sized object with the mass of our Sun, spinning rapidly and wrapped in a magnetic field 1 trillion times stronger than Earth. A starquake on its unthinkably dense surface, or a sudden reconfiguration of that impossibly powerful magnetic field, could theoretically unleash a catastrophic burst of radio waves in an instant. Other possibilities include the cataclysmic merger of 2 neutron stars, or the violent destruction of a star as it is shredded by a black hole. Some FRBs even repeat, firing off multiple bursts from the same location over days or years, which rules out one-time destruction events and points to a source that can survive its own outburst, like a volatile, spinning magnetar. But the true power of these cosmic flashes is not just in their source, but in their journey. As an FRB's signal races across the universe, it passes through the diffuse gas and plasma that fills the space between galaxies. This material, thin as it is, leaves a fingerprint on the burst. Lower frequency radio waves are slowed ever so slightly more than higher frequency ones, an effect called dispersion. By measuring this dispersion, astronomers can calculate the total amount of ionized material the signal has traveled through. This turns each FRB into a cosmic probe. When we detect one from the early universe, its radio waves have passed through the fog and clearing bubbles of the reionization era itself. By analyzing the signal's dispersion and how it has been scattered, we can map the density and ionization state of the intergalactic medium across cosmic time, offering a direct measurement of how the universe cleared its skies. Furthermore, FRBs are providing a critical clue in solving another mystery: the location of the universe's missing baryons. You will recall that baryons are the ordinary matter particles, protons and neutrons, that make up stars, planets, and us. While we can account for the baryons locked in galaxies and clusters, a significant portion, perhaps as much as half, is unaccounted for. Theory predicts it should be floating in a warm, hot, diffuse web of gas between galaxies, but this gas is too thin and too hot to glow in any light we can easily see. An FRB's signal, however, passes right through it. By using distant bursts to measure the total amount of ionized material along its path, astronomers are finally weighing that elusive cosmic web, confirming that the missing baryons are indeed there, hiding in the darkness between the galaxies. Each brief, brilliant flash is therefore a messenger carrying encoded information about the vast, empty spaces it has traversed. They are both a profound mystery of their own and a revolutionary new tool, allowing us to sense the invisible scaffolding of the cosmos and listen to the faint echoes of the universe's stormy youth. These brilliant radio flashes are not the only high-energy messengers crossing the cosmic void. Some carry a punch so immense it defies the very laws that govern their journey. The 20th mystery confronts us with the GZK horizon and the puzzle of ultra-high-energy cosmic rays. Cosmic rays are not rays of light, but atomic nuclei, the stripped cores of atoms, hurtling through space at nearly the speed of light. Most come from within our galaxy, accelerated by shock waves from supernova explosions. But a tiny fraction, the ultra-high-energy cosmic rays, possess energies millions of times greater than anything our most powerful particle colliders can produce. A single one of these subatomic bullets carries the kinetic energy of a professionally thrown baseball, all compressed into a particle smaller than an atom. The mystery is not just their existence but their arrival. In 1966, physicists Kenneth Greisen, George A. Zatsepin, and Vadim Kuzmin calculated a fundamental limit for such particles traveling across the universe. They realized that the cosmos is not empty. It is filled with the faint relic photons of the cosmic microwave background, the afterglow of the Big Bang. For a proton or atomic nucleus traveling at over 99.9999% of light speed, these harmless microwave photons appear as a barrage of high-energy gamma rays. When such a particle collides with one of these background photons, it triggers a reaction that robs it of energy, producing new particles in the process. This interaction acts like a cosmic fog, a gradual but inevitable braking system for the most energetic travelers. The GZK limit states that any proton from a source farther than about 150 million light-years away should be slowed below a certain energy threshold by the time it reaches us. It creates a horizon, a sphere beyond which the most extreme cosmic rays cannot penetrate. Yet our detectors here on Earth, like the Pierre Auger Observatory in Argentina, have recorded a handful of these particles with energies clearly beyond the GZK limit. It is as if someone threw that baseball from another continent, but it arrived with the same force as if thrown from across the street, having somehow ignored all the air resistance in between. So how are they getting here? One possibility is that they are coming from very nearby, astronomically speaking. Within our local cosmic neighborhood, within that 150 million light-year horizon, there may be engines of unimaginable power capable of such acceleration. Candidates include active galactic nuclei with their supermassive black holes, or perhaps catastrophic events like the merger of neutron stars. The trouble is, when we trace the rough direction of these ultra-high energy events back into the sky, we do not find any obvious, monstrous sources sitting right on our doorstep. The other, more thrilling possibility is that our understanding of the particle interaction itself is wrong. Perhaps at these extreme energies, protons interact with the cosmic microwave background in a new way not described by our current models. This could point to new physics beyond the standard model of particle physics, a change in the fundamental rules that govern how matter and energy behave at energies we can never hope to recreate in a laboratory. These particles are our only direct samples of such extremes. Detecting them is a monumental task. They are incredibly rare, striking a given square kilometer of Earth's atmosphere only about once per century. When one does hit, it collides with an air molecule high in the atmosphere, triggering a cascading avalanche of secondary particles, a vast, invisible shower that spreads over miles. Giant observatories like Pierre Auger use thousands of water tanks to detect the faint flashes of light these secondary particles produce as they spread across the landscape, or use telescopes to watch the faint ultraviolet glow the shower leaves in the night sky. Each detection is a precious data point, a cosmic bullet whose energy and direction we must measure with exquisite care. They are messengers from the most violent processes in the universe, carrying encoded information about forces that can tear atoms apart and hurl their cores across the cosmos. The fact that some of them appear to have broken the universal speed limit for their journey only deepens their intrigue, suggesting that either our map of the local universe is missing a colossal landmark, or the laws of physics have a footnote written in energy we are only beginning to read. While those ultra-high energy particles race through the void, the universe itself is not a random scattering of lights. It is a masterpiece of architecture woven into a pattern of breathtaking scale and elegance. The 21st Great Mystery asks how the faintest whisper from the quantum dawn grew into the cosmic web. This is the large-scale structure of the universe, a vast three-dimensional tapestry of galaxies. On the grandest scale, galaxies are not sprinkled randomly like salt. Instead, they are strung along immense filaments like beads on invisible strings, stretching for hundreds of millions of light years. These filaments intersect at dense nodes where thousands of galaxies swarm in massive clusters, and between these luminous threads and knots lie the cosmic voids, immense, nearly empty bubbles of space that can span hundreds of millions of light years across. This structure, when mapped, resembles a neural network or a froth of soap bubbles on a scale beyond human comprehension. Its origin story begins with the tiniest of seeds, the quantum fluctuations imprinted on the universe during its first split second of existence during cosmic inflation. Inflation took these microscopic, random ripples in the fabric of space-time and stretched them to cosmic proportions. After inflation ended, these ripples existed as slight differences in density, tiny hills and valleys in the otherwise smooth distribution of matter and energy. They were the blueprint for all future structure, but a blueprint is not a building. For that, you need a construction crew, and the foreman was dark matter. Because it is cold, meaning its particles moved slowly, dark matter began to clump first under its own gravity. Those slight density variations from inflation acted as focal points. Over hundreds of millions of years, dark matter collapsed into a vast, invisible scaffold, a web of filaments and halos. Ordinary matter, the atoms that make up stars and galaxies, was late to the party. For a long time, it was too hot and energetic, buffeted by the pressure of light. But once it cooled enough, it began to fall into the gravitational wells carved out by the dark matter. This is where the story gets beautifully complex. Gravity pulls the gas in, but as it falls, it can collide, shock, and heat up, resisting further collapse. The first stars that ignite within these clouds blast out radiation and powerful winds, pushing gas back out. Supernova explode, enriching the gas with heavy elements and stirring it violently. And at the centers of growing galaxies, supermassive black holes switch on, their quasars pouring out unimaginable energy that can heat or blow away an entire galaxy's worth of star-forming fuel. This interplay, known as astrophysical feedback, is a constant tug of war. Gravity wants to pull everything together to build ever larger structures, while the energy from stars and black holes fights back, regulating the process and preventing all the gas from turning into stars at once. It is this delicate balance that determines how many stars a galaxy forms, how big it grows, and even the shape it takes. To map this grand design, astronomers undertake monumental surveys. Projects like the Sloan Digital Sky Survey have painstakingly measured the positions and distances of millions of galaxies, using their light to create a three-dimensional chart of the cosmos. The resulting maps are stunning, revealing the filamentary web in exquisite detail. We then compare this real map to the predictions of supercomputer simulations, which model the growth of dark matter and the messy physics of gas, stars, and black holes from the first moments to the present day. The match is remarkably good, a triumph of modern cosmology. Yet discrepancies remain in the finer details, the exact distribution of galaxy sizes and shapes within the web. These tiny mismatches are where the next clues lie, hinting that we may still have something to learn about the nature of dark matter, the strength of feedback, or even the initial conditions laid down by inflation itself. The cosmic web is the ultimate expression of order born from chaos, a pattern written in galaxies that tells the story of everything, from a quantum whisper to the gravitational symphony of the dark. That vast cosmic web, woven from dark matter and lit by galaxies, has its origin story written in a realm 1 trillion times smaller than an atom. The blueprint for everything we see was drawn by quantum mechanics in the first fleeting moment of existence. During the inflationary epoch, when the universe expanded faster than light, the vacuum of space was not truly empty. It was a seething quantum foam where pairs of virtual particles and antiparticles constantly flickered into and out of existence. These were not particles of matter, but fluctuations in the very fabric of space-time itself, tiny hills and valleys in the energy field that drove inflation. In that hyper-expanding environment, a remarkable thing happened. A microscopic quantum fluctuation, born on a scale 1 billion times smaller than a proton, did not simply vanish back into the vacuum. As the space around it inflated exponentially, the fluctuation was stretched along with it, frozen into the geometry of the cosmos. What was once a random, subatomic quirk became a macroscopic variation in density, a region ever so slightly denser or less dense than its surroundings. Imagine drawing a tiny, intricate pattern on a deflated balloon. As you blow the balloon up to the size of a house, the pattern expands perfectly, preserving its shape but now writ large across a vast surface. Inflation did exactly that to quantum noise, magnifying it to the scale of the observable universe. These imprinted ripples are the primordial density fluctuations, the seeds from which all structure grew. The slightly denser patches had a tiny gravitational advantage. Over the next several 100 million years, dark matter and then ordinary matter were pulled toward these spots, beginning the slow gravitational collapse that would eventually form the first stars, galaxies, and the magnificent filaments of the cosmic web. This theory is breathtakingly elegant because it connects two utterly disconnected realms of physics. The bizarre, probabilistic rules that govern particles on the smallest scales are directly responsible for the grand architecture of the cosmos on the largest. It makes a powerful, testable prediction. If the initial seeds were truly quantum in nature, they should have been distributed randomly, producing a specific pattern of hot and cold spots in the cosmic microwave background with a particular statistical signature, like a specific type of static. This is precisely what satellites like WMAP and Planck have observed with stunning precision. The pattern of fluctuations in the CMB matches the prediction of quantum origin almost perfectly. Yet for all its success, this story leaves a profound gap. We know the quantum fluctuations were stretched by inflation, but we have no idea what the inflationary field actually was. What was the nature of that strange energy that powered the universe's hyper-expansion? Was it a fundamental field associated with gravity itself, or something entirely new? The details of this field determine exactly how those quantum ripples were imprinted, influencing the subtle statistical properties of the CMB and the eventual distribution of galaxies. We see the magnificent, stretched-out pattern, but the original brush that painted it remains hidden in the physics of an energy regime we may never directly access. It means the entire visible universe, with its hundreds of billions of galaxies, may be the magnified fingerprint of a single, random quantum event, a cosmic lottery win whose first cause is still a mystery written in the smallest script imaginable. Those quantum seeds gave us the universe we see, but they also point to a relic that should be everywhere, yet is nowhere to be found. Our 23rd mystery is the curious case of the missing magnetic monopoles. According to our best theories of how the fundamental forces of nature once behaved, the searing heat of the early universe should have forged staggering numbers of these bizarre objects. A magnetic monopole is exactly what it sounds like, a particle that is just a north magnetic pole, or just a south, wandering through space completely alone. This is utterly unlike any magnet we have ever seen. Every magnet from a child's toy to the Earth itself comes as a dipole with inseparable north and south poles. Cut a regular magnet in half and you do not get isolated poles, you get two new, smaller dipoles. But the grand unified theories, which attempt to describe how the electromagnetic, weak, and strong nuclear forces were once a single, unified force, demand that monopoles exist. In the unimaginable energy of the first moments after the Big Bang, as the unified force began to cool and split apart, the fabric of space-time itself would have undergone a phase transition. Think of it like water freezing into ice. As liquid water cools, it crystallizes, and where different ice crystals meet, defects like cracks or boundaries form. In that early cosmic cooling, similar defects would have formed in the fields that govern physics, and these defects would manifest as monstrously heavy, stable particles, the magnetic monopoles. These would not be ordinary particles. A single magnetic monopole could weigh as much as a bacterium, which is colossal for a fundamental particle, and it would carry a magnetic charge billions of times stronger than anything we can produce. The problem is one of overwhelming abundance. The standard Big Bang model without inflation predicts that these monopoles would have been produced in such incredible numbers that they would dominate the mass density of the universe today. We should be tripping over them. Their collective mass would have curved the universe into a ball and caused it to collapse long ago, and their powerful magnetic fields would be unmistakable in our experiments. Yet, despite decades of sensitive searches, from deep underground labs to scans of moon rock and ancient minerals, not a single definitive magnetic monopole has ever been found. They have simply vanished. This glaring absence is one of the strongest motivations for the theory of cosmic inflation. The proposed solution is elegant and powerful. If immediately after those monopoles were created, the universe underwent a period of hyper-fast expansion, the density of these relics would have been diluted to practically zero. Imagine you have a handful of confetti in a small room. That room is then suddenly stretched into the size of a continent. The confetti is still there, but it is now so fantastically spread out that finding a single piece becomes astronomically unlikely. Inflation did exactly that to the monopoles. It took that early, dense soup of defects and stretched space itself so dramatically that the average distance between any two monopoles became larger than our entire observable universe. They were not destroyed, they were simply scattered into the cosmic vastness beyond our horizon. For all practical purposes, from our perspective within our observable bubble, they are gone. This is why the monopole problem is such compelling, if indirect, evidence for inflation. The theory was not invented just to solve this one issue, but it provides a beautiful, natural answer to a major puzzle that the classic Big Bang model could not explain. It tells us that the universe we can see is just a tiny, smoothed-out patch of a much grander reality. A patch where the relics of a violent unification were swept so far into the distance that we may never find them. The silence of our detectors, the empty searches, thus speak volumes, echoing a moment of unimaginable stretching that cleared the stage for the universe we recognize today. The profound order of the quantum seeds and the absence of monopoles point to an even deeper, more fundamental peculiarity about our beginnings. The early universe was not just smooth and flat, it was in a state of astonishingly low entropy. Entropy is a measure of disorder, of randomness. The second law of thermodynamics tells us that entropy in a closed system always increases over time. This is why ice melts in a warm room, why perfume disperses, and why we remember the past but not the future. It is the physical reason we perceive an arrow of time. A state of low entropy is a state of high order, and the Big Bang presented us with the most ordered state imaginable. All the mass and energy of the cosmos was packed into an unfathomably hot, dense, but remarkably uniform state. Think of a brand new deck of cards perfectly sorted by suit and number. That is low entropy. Shuffle that deck once, and you increase its disorder. The entire history of the universe, from the first stars to the last dying embers, is the story of that cosmic deck being shuffled. The formation of galaxies, the birth of solar systems, the evolution of life, all of these complex structures are possible only because we started with that incredibly ordered, low entropy condition. If the universe had begun in a state of high entropy, a state of maximum disorder, it would have been a thin, lukewarm soup of particles evenly spread throughout space, with no density differences to create gravity, no temperature gradients to drive any process, and certainly no possibility for stars, planets, or observers. The mystery is not that entropy increases, that is a basic law. The profound puzzle is why it was so low to start with. This is arguably the most fundamental question about our origins. Why did time have such a clear starting point with the universe in this exquisitely special configuration? One perspective is that this is simply a brute fact, an initial condition with no deeper explanation. The universe began this way because it began this way. But to many physicists, a state of such spectacularly low probability demands an explanation. Some theories suggest our observable universe is just one region within a much vaster, perhaps eternal, multiverse. In this unimaginably large ensemble of universes, most would be high-entropy messes, but by sheer chance a tiny fraction would, through random fluctuation, find themselves in a low-entropy state. We, of course, can only exist in such a rare, ordered bubble. Our entire cosmic history is just a statistical fluke within an endless, mostly disordered eternity. Another compelling idea is that of a cyclical universe. Perhaps the Big Bang was not an absolute beginning, but a transition from a previous phase. In some cyclic models, the universe undergoes endless cycles of expansion, contraction, and rebirth. Each cycle ends in a high-entropy state, a featureless expanse, but a proposed cosmological constant or dark energy could drive a kind of cosmic reset, smoothing and stretching that chaos into a new low-entropy state for the next cycle. In this view, the arrow of time reverses direction at the bounce, and our low-entropy beginning was the natural outcome of the cycle before. This mystery is intimately tied to the nature of the Big Bang singularity itself. That point of infinite density represents the ultimate state of minimal entropy, the starting line for time's arrow. Understanding what, if anything, came before that singularity, or what laws governed its formation, may be the only way to answer why our story started with such a pristine deck of cards. Every structure we see, every process that unfolds, from the nuclear fusion in stars to the firing of neurons in our brains, is a consequence of that initial order slowly, irrevocably running down. We are not just living in the aftermath of the Big Bang, we are living in the long, slow sigh of its extraordinary initial state, riding the arrow of time that it alone provided. That pristine low-entropy beginning might not be a singular miracle, but a common occurrence in a reality far grander than our own. The final and perhaps most speculative mystery asks a question that redefines existence itself. Is our universe unique? The concept of the multiverse suggests the answer is a profound no, that our cosmos is just one bubble in an infinite, frothing sea of universes, each with its own distinct laws and history. This idea does not spring from pure imagination, but emerges naturally from the edges of our most ambitious theories. Take the mechanism of cosmic inflation. Many models suggest that once inflation starts, it is eternal. The repulsive energy driving the expansion can decay in some regions, creating stable bubbles of space like ours where inflation ends, allowing for stars and galaxies to form. But in between these bubbles, the inflationary energy persists, creating more space at a staggering rate, which in turn spawns more bubbles. This process would be unending, generating a limitless multiverse of pocket universes within an ever-expanding inflationary background. String theory, a candidate for a theory of everything, adds another layer. It suggests the fundamental constants of nature, like the strength of gravity or the mass of an electron, might not be fundamental laws but accidental outcomes. They could be determined by the way extra, curled-up dimensions of space are shaped. The theory allows for a colossal number of possible shapes, perhaps 10 to the 500, each corresponding to a different set of physical laws. In an eternally inflating multiverse, every possible shape, and thus every possible set of laws, could be realized in some distant bubble. This provides a dramatic answer to a haunting question we have encountered throughout our journey. Why is our universe so finely tuned for life? The strength of dark energy, the precise balance of matter and antimatter, the exact nuclear forces that allow carbon to form, all seem delicately calibrated. If any one of these numbers were slightly different, atoms would not hold together, stars would not burn, and life would be impossible. In a single, unique universe, this perfect tuning feels like an unbelievable coincidence. But in a multiverse where every possible combination of constants exists somewhere, it is no longer surprising that we find ourselves in one of the rare, life-friendly bubbles. We could not exist anywhere else. This is the anthropic principle in a cosmic context. Yet, for all its explanatory power, the multiverse presents a formidable scientific challenge. By definition, these other universes would be beyond our cosmic horizon, causally disconnected from us forever. No signal, not even light, can cross the inflating space between bubbles. This raises a critical question. If we can never observe or interact with these other realms, can the multiverse ever be more than a fascinating philosophical idea? Scientists are searching for indirect, testable signatures. Perhaps the collision of our bubble with a neighboring one in the distant past left an imprint on our cosmic microwave background, a circular pattern like the cold spot we discussed. Or maybe the peculiar way our universe inflated left a statistical fingerprint in the distribution of galaxies that points to a larger multiversal structure. So far, no such evidence is conclusive. The multiverse remains a breathtaking extrapolation of our best physics, a logical possibility that stretches the meaning of reality. It suggests that every cosmic story we have told, from the quantum seeds to the fate of dark energy, might be just one narrative in an infinite library of possibilities, where other universes live out entirely different laws with no stars at all, or where gravity is repulsive, or where time flows backward. It is the ultimate mystery because it places our entire cosmic journey within a context so vast it may forever lie beyond the reach of observation. A final, humbling reminder that the greatest secrets of the early universe might point to realities we can only imagine. From the quantum whisper that seeded galaxies to the ghostly pull of dark matter holding them together, we have journeyed across the profound unknowns of our origins. These 25 mysteries are not just gaps in a textbook, they are the very frontiers of human understanding, the edges of the map where our knowledge dissolves into wonder. Each one, from the impossible speed of ancient black holes to the chilling silence where magnetic monopoles should be, represents a fundamental question about the nature of reality itself. We have seen how the universe's first moments set a stage of improbable perfection, how titanic stars forged the elements of life in their violent hearts, and how dark energy now silently dictates our cosmic fate. This story, woven from mathematics and starlight, is the greatest detective story ever told, and we are all part of it. The most thrilling chapter is being written right now. With eyes like the James Webb Space Telescope piercing the cosmic dawn, and ears like future gravitational wave observatories listening for the ripples from the first black hole collisions, we are on the verge of revelations that could rewrite our cosmic history. The answers are out there, waiting in the faint glow of the first light and the quiet geometry of empty space. So stay curious, look up, and remember that every point of light is part of a mystery 13.8 billion years in the making. We want to know which of these cosmic puzzles captures your imagination the most. Is it the baffling nature of dark energy, the search for the first stars, or the mind-bending possibility of a multiverse? Let us know in the comments below, and if you crave more journeys to the edge of understanding, subscribe to explore further into the wonders of space and science.